So I just want to show you where we are in Galway. So this is probably the last university in Europe. It used to be the edge of the known world. Right? After that, there is some new places, New York, Boston, those kind of places. But, so I guess in the Middle Ages, when Europe was in some difficulty, the education that came to Ireland somehow came back. You know, the bad guys never got as far as Galway, so good news, and were able to send their monks and so on back to Europe after the the Dark Ages, what we call the Dark Ages. Anyway, it's quite a trip here. You'll be glad to know I did not take the car here, because I'm coming via St. Petersburg and Moscow and somehow here. Anyway. So in my lab, we work on microcirculation imaging and have been doing that for a while. And we started with laser Doppler, which is a method for single point measurement of the movement of blood flow. And that was started in the 1970s by a guy called Mike Stern, published a paper in Nature where he used laser light into the tissue. It bounces around inside the tissue, it gets scattered. We will talk a little bit about scattering of light. And by the way, I will try to put something for engineers and physicists, so some physics, but also hopefully there's something of interest for the clinicians among you. So the light goes into the tissue and it bounces around. Actually, I can do this here very nicely. You can see on my finger, if I shine a point of light on my finger, you see there's a big even glow. And if it was dark enough, you would see, maybe you can already see that there's a glow coming out the other side, but you don't see any shadow for the bone, right? Does the light go through the bone? It doesn't go through the bone, so why is there no shadow? Because of the scattering. So the scattering is really very strong. There's quite a large bone, but you don't even notice that there is a bone because the scattering is really very strong. And so after 1 millimeter, we say the light is diffuse. It's like molecules bouncing around in a bucket. You know, our kids in the playground on sunny Friday afternoon, they're really in their top element bouncing around the place. So really, the light has no memory of its original direction. Now it's going in every direction after 1 millimeter. So that will become important to our understanding of how light interacts with the tissue. Because we think a lot about absorption, light getting absorbed and giving us colors in that way, but scattering in human tissue and animal tissue is much more important, about 100 times bigger effect than absorption. So that was laser Doppler, and then laser speckle is interesting. It's related to laser Doppler, but it gives us faster pictures, and so we can have movies, and it's much simpler. Then the problem with these methods, I guess, is that they're sensing movement. So any movement will cause a Doppler shift or a change in that signal. And so if you're imaging a moving animal that is breathing, or you're trying to image on the lungs of a mouse or whatever, then you have a lot of problems with movement artifact. So the whole tissue is moving, so that gives you a Doppler movement, and the blood flow is moving inside that gives you a Doppler movement. It's difficult to tell the difference between the two, so you have a noisy image. With this third one, the idea was to avoid that movement and produce pictures of the concentration of red blood cells in the tissue without, so you can see it here, without the use, without the problem of this movement. And this is an even simpler technique because it's just a red, green, and blue camera. So I will tell you a little bit about how that works later. And because it's so simple, you can implement it on a mobile phone. Okay, and I can even show you on my phone that app using that technique, or you can download it yourself. Then we started to work on optical coherence tomography because the clinicians, like Ferenc Barry, are always asking us, well, okay, these are nice pictures, but where in depth is this movement? Is it in the nutritional flow, close to the surface, or is it a really thermoregulatory flow, you know, the heat dissipation flow, which is maybe deeper in the tissue, and you can't tell. This is an integration of all the depths that the light comes from, so it's maybe one, you can think about it as a layer of 1 millimeter, but you don't know where in the layer the signal is coming from. With optical coherence tomography, you can tell exactly what depth, so you can slice everything in depth. So optical coherence tomography is like ultrasound, like clinical ultrasound, except that the depth now is 1 millimeter instead of 10 centimeters, and the resolution is 10 microns instead of 1 millimeter. Okay, and we will find actually that depth and resolution are very closely connected. And this is probably the strongest point I want to make in my talk today about the connection between how deep you can see and what resolution you get when you try to look deeper. So I said that this one is limited to 1 millimeter optical coherence tomography. We can make these kind of maps. Okay, I don't know if we can make it a little bit darker. Could somebody pull the one at the back? You can see a little bit better the vessels here. And so this is my forearm, and if in my forearm I look at this little red square here, inside that red square we have lots of little blood vessels, and those blood vessels have a diameter of maybe 20, maybe 50 microns, that sort of range, okay, in the first millimeter of the tissue. And actually quite a lot of them are not open all of the time. In fact, there's a much better expert here than me, but probably 1 in 4 are open in normal circumstances. So there's a huge capacity to increase your blood flow in your skin. And in fact, that's important for maintaining your blood pressure. Why? Does anybody know why that helps to maintain blood pressure? We have a lot of clinicians. Somebody should know. Because you can dump a lot of blood into the skin, you can push it out into the skin if you want to lower your blood pressure, I guess, and you can pull it back. You can close down these blood vessels and pull that blood back into your central system. Now, I shouldn't say so much about clinical stuff in front of other people because I'm just a physicist, right? So I should be careful, I guess. But you can tell this if you have a cut or a deep wound, or even if you get really scared, what happens? You go white in your face. Yeah. So all that blood that was in your face is sucked into the core to increase the pressure and make sure you have that pressure in the core. This picture here is from this technique, which is just a simple red, green, and blue camera. But the idea is to see where is the most severe burn, and you need to make a decision about, do you take some skin from the tummy here, from the stomach, or will some of the skin will repair itself, okay, if it's not too deep a wound, but in some areas you need to take some skin from maybe here to repair that. This guy is 2 years old and he pulled a boiling kettle on him, so not a dangerous, big, scary laser, but a kettle that you find in every house. Okay. So if we want to see deeper than 1 millimeter, we need to use photoacoustic imaging or some other form of diffuse light. This scattered light that I talked to you about, this kind of light. Because after about 1 millimeter, only 1 in a billion, 1 in 10 to the power of 9 photons are coming back directly to the surface, right? Straight in and straight out, 1 in a billion. Straight in, bouncing around, and coming back, maybe 1 in a 10,000. Okay, so there's a difference between diffuse light coming back and this optical coherence tomography, which is an interference technique. It's looking only for light that went straight in and came straight straight back. Ballistic photons, we call them. Okay? We published a book which collected the thoughts of many of the people who are working in this field in various areas, developing technologies. So you can check that from Wiley, and it covers all of the areas that I'm going to talk about today. More up to date are two reviews that we did, one in 2013 in the journal Biophotonics, and here is one that's really only published last week, so in the journal, the Microcirculation journal, actually also a Wiley journal, so you can check those. So in the beginning, when people first saw red blood cells, they started to draw images like this, and this is a drawing from Malpighi, a very famous professor in Bologna. There is a story that he actually saved the University of Bologna, which had 116 students and 100 professors. And the reason this saved the university was that he proved for the first time that blood flows from the arterial side to the venous side through little capillaries by looking in the frog's lungs. So Harvey, many of you will know, William Harvey had this theory that blood flows in the arteries, and then he could see blood flowing in the veins, and he knew that somehow this blood must come from the arteries to the veins, but he never really worked out how, and actually didn't have this concept that there would be some small vessels between the arteries and the veins. Now it seems like that's obvious, they must be going, but you have to remember when you're at the other side of this discovery, these things are never so obvious. So people didn't really understand that, and it had some resistance, let's say. But the fact that you could actually see it made it much easier for Malpighi to have his work accepted. And the reason Malpighi was able to do that, Malpighi is in Bologna, in Italy, and if I go back to my map, actually, I can show you roughly. Somewhere over here is Bologna, and somewhere up here, sorry, up a little. Here? No, here?
Close to Milan.
Yeah,
Close to Milan.
Yeah.
Ah, here. So somewhere here, I guess. Very specific. Okay, anyway, somewhere over there. And somewhere over here, there was another very famous guy called Van Leeuwenhoek. Van Leeuwenhoek discovered how to make the microscope. Actually, there was somebody much closer, Galileo, who had done the telescope, and everybody thought, well, if you have a telescope, it's very easy to make a microscope because you just turn it backwards and you should see very small things. Do the physicists know why that doesn't work? Because of optical aberrations. Okay, there are just too many aberrations and it never really worked properly like that. But this guy, who was a tax collector over here in the Netherlands, discovered how to make a microscope. And he actually had a lot of battles with the Royal Society in England at that time, in London at that time, about this. And they really fought very hard against believing that this microscope was really working. He's looking at single-celled organisms, an amoeba, and they didn't believe any of this stuff. Eventually they sent a delegation over, so from London over to here. This is in the 1600s, I think. I hope I'm right. In the 1600s. So sent a delegation over here to find out what about this tax collector in the Netherlands who suddenly appears and is telling us that he has found single-celled animals. So he does that, and how did he make the microscope? He was being a little bit secretive about it, but because he wanted to protect his idea, I guess, or something. But in any case, he just made a microscope with a single lens, I should say, single lens. And the way he got the very high magnification was to make a very small glass ball. So he was giving the impression to everybody that he was spending his evenings polishing lenses for a long time and getting these wonderfully smooth, excellent lenses. But actually what he was doing was melting glass and getting a very, very small ball. And if you have a very small ball, you have a very high numerical aperture. And he put this small lens just onto a holder and looked through the lens, and you can see the cells. Okay. At least, that is how I understand the story. And so, even though this picture was drawn by Malpighi in the 1600s, and is a very good image of what we now understand to be red blood cells, how they look like, it's actually very difficult to see that inside a human being, even with the extraordinary microscopes that we have today. Okay? Very, very difficult. In fact, I think it's, well, except in very unusual circumstances, you will never see this inside a human being. So that's back in the 1600s, and Malpighi didn't publish very much, which is unfortunate, because it would have been nice to see more of what he published. But the good news is that the University of Bologna is still in business. Very shortly after Malpighi's work, the number of students went up to 10,000. Okay, I don't know how shortly after, but anyway, I like to tell that story because the university is constantly telling me that research is a drain on the university. And, you know, the accountants are always saying you're costing money, but actually, without research, the university cannot exist. It cannot be a university because you cannot teach anything new. So, in the 1960s, people started to work a lot on microcirculation, and the idea of microcirculation starts to get mentioned in the literature a lot. One of the first people to mention it was my PhD supervisor, a guy called Terence Ryan, who's now extremely old, but still going, giving plenary lectures in all kinds of places in the world, he tells me. But he published a paper in, I think, 1965, or not the first, exactly the first one, but maybe second or third one on this list. And so you can see that the number of publications grew rapidly, very rapidly here in the 70s, because people started to look not just with microscopes, but to add cameras. And not just cameras, but video cameras. And if you have a video camera, you know how far a cell has moved from one frame to the next. So now you can tell how fast is the blood moving. You can tell the velocity of the blood. So video development in the 1970s and TV had a huge impact on microcirculation research. Then it gets flat for a little bit. Then the laser Doppler machines and so on come out here, and it goes on. And if we look at the technical development, which I'm using the publications in physical science journals and engineering journals to kind of get a gauge, some feeling for how much technical development is going on. You can see that there's quite a bit here, with some kind of bump here in the middle of the 1970s, just after Mike Stern produces his seminal paper in Nature about laser Doppler. And then it's kind of flat for a while. But in the last few years, you have this massive increase relative to the total number of publications in microcirculation. So something in the technical journals is increasing an awful lot. And I think that that is because we can now see microcirculation in 3 dimensions and in 4 dimensions. The 4th dimension is time, so videos of blood flow. So I will try to talk a little bit about those. And you can see videos like this. These horizontal capillaries are unusual, and they really only exist on just above the nail fold. So that little piece of skin that comes across the top of your nail is only in that direction, so the vessels must go out and come back. Usually the blood vessels are coming up to the surface and going back down in these papillary loops. But this is unusual, and it's an easier place to see blood flow. We're not really seeing cells. You can kind of make out that there's some blob moving, but you don't see what Malpighi drew in that. And so the microcirculation is performing some key functions. The exchange, giving out nutrition, taking back waste, regulating the body temperature. It performs some of that, but bigger vessels and AV shunts that bring, shunts are short vessels that bring blood flow directly from the arterial side to the venous side without going through the capillaries. And this is designed where you need to lose a lot of heat. When it is very hot outside, your forehead, the palms of your hands, the soles of your feet, they all get a lot of blood flow going to there from the core, so they're sending out all that hot blood out to those regions, and the capillaries are not enough in that scenario. And I already talked about regulating blood pressure. They have some structural problems during diseases like diabetes, Raynaud's syndrome, which is where you get these white fingers. It's slightly different to vibration white fingers, but in cold weather, some people get some extreme effect of white fingers. In cancer, in fact, the word cancer, any Greek people here? Does anybody know what the word cancer comes from?
No.
The crab.
Crab, yeah.
The crab. Yeah, so it comes from the crab. And the idea of the reason that it comes from the crab is that the crab's claws look something like this. And when people first started to look at cancer, they could see that there are vessels in this kind of shape around, growing around the tumor. So it's an unusual shape of these blood vessels. So it's actually related to the blood vessels. The structure of the blood vessels is different in cancer than in normal conditions. And they grow much faster, and they have some different properties which you can use to tackle cancer to some extent. Although it has turned out to be not as successful as people thought originally, I suppose, which is a pity. Here is probably the most, the most that the sort of microscopic view has progressed with just using microscopes, light microscopes, to look at blood vessels. And the innovation, I suppose, two innovations. One is to use green light, which is very strongly absorbed by blood, by hemoglobin. So you get these dark streaks wherever you have blood vessels. And the second innovation is that it is what we call dark field imaging. So the problem with shining a light on something and looking directly at where you shine the light is that you get a glare from the surface. You get a bright reflection from the surface, so you can't. It's harder to see what's going on underneath. If you shine the light, as this system does, through this special lens, which is just around the outside. Okay, so the light is just coming through this part all the way around, and it's not going directly to the center. So it comes in here, bounces around, interacts with the blood vessels, and comes back to the surface. So you're not looking directly where you shine the light, you're looking in the so-called dark field. Of course, it's not completely dark, because if it was completely dark, you wouldn't see anything at all. But you have some photons coming back where there are no blood vessels, not so many photons coming back where there are blood vessels, because once they hit the blood vessels, they're absorbed very strongly. Okay? The other place that you can see blood vessels in a human being are in the eye, and that's because the eye is designed to get light in, and of course, if light can go in, it should be able to come back. So, if you look at the retina, and this is my retina, and so you can see the fovea here and the blood vessels, the retinal artery and so on. Oops. Here. And it is easier to see that in the eye. Now, having said that, this was done with quite a fancy, very low angle Heidelberg scanning laser, and the whole image was not taken in one go. It was taken in 16 different images, and they're stuck together. Because if you try to you see the whole field of view, you're limited by the numerical aperture of the human eye, and that's not very good to get high resolution images. Okay. This was actually done, and I was being fed high levels of oxygen to try to see if my blood vessels were able to adjust for that. I never got the result of this because of the ethical setup. The subject should not be told what's going on, so hopefully my eye is healthy enough. So here's a demonstration of fluorescence microscopy, and you can see that if you tag red blood cells with GFP, green fluorescent protein, you can get very bright and very nice images. We go back to the surface here again. So that was zoomed in, and we're now zooming back out. So we can very easily see the blood vessels. So the advantage of fluorescence is that it's much brighter. And the second advantage with fluorescent light is that you're only dealing with the light going in one direction, right? Because you can fill the whole area with light, and wherever it is absorbed in the dye, it gives out a different photon, and that photon is coming back to the surface. So the green photon is coming out. You put in a blue photon and you get a green photon out, green light out, blue light in. Usually we have to shine the light in, and we have to try and avoid it being scattered on the way in, and we have to avoid it being scattered on the way back out. But with fluorescence, we only have to worry about it being scattered on the way back out. So you have a one-way scattering problem. Even so, and even in this relatively transparent medium, this is a mouse embryo, which is a few days old. I don't know exactly how many, but you can see the beating heart already here. And actually, if you look at the work of Irina Larina from Baylor College of Medicine, they now have beautiful 3D images with OCT without using fluorescence of the developing beating heart, which is really nice. The problem here is that, okay, this is at about 30 microns from the lens. If you go deeper, now we are about 100 microns, more than 100 microns from the lens. We see almost nothing, just a blur. Okay, so scattering is a huge problem, and fluorescence microscopy only works in the first 100 microns. Okay, so we're only able to see in about 100 microns. So you can get beautiful images of cells on Petri dishes, and you can get beautiful images within 50 microns of the surface. But if you try to see deeper than that, you have a big, big problem. Okay? And that's a common problem all the way through all kinds of imaging, which I want to convince you of today. When I started in this business, we looked at using our laser Doppler equipment to assist in the development of antivascular drugs like cumbrastatin. Statins are used for all kinds of things. Now, I think clinicians recommend them for almost general use for preventing problems with cancer. But in any case, the idea was that you have a tumor like this, and that tumor has grown very rapidly, and the blood vessels in there have, along the walls, they have endothelial cells. Endothelial cells are lining the walls, and because that blood vessel has grown so rapidly, those endothelial cells are immature, and the membrane of the endothelial cells are a little bit leaky, so they will allow some drugs to go across the membrane. And if you have a drug that will go across the membrane and kill the blood vessel essentially, or damage the endothelial cells, then if it's only doing that in the blood vessels in the cancer and not in the normal tissue, that seems like a nice way to kill a tumor. So here's the idea. You inject the drug, it goes into the endothelial cells swell up and they choke the cancer. Nice idea, we published it in 1996. The company, Oxygene, is still alive, but it's never sold anything. And they're still hoping that they have an application in thyroid cancer. So they've been through many levels of clinical trials in the meantime. So they went on from clinical trial stage 1, stage 2, stage 3, and now they're trying to see if the drug is still alive, but the company is still alive in any case, so it seems. But it does show how long it takes to take an idea drug like this into the clinic. Right? This is already proven in a mouse. Before that, there's in silico development, right, where you have thousands, hundreds of thousands of drugs. You come down to maybe 100 drugs, then you come onto Petri dishes with cells, and you come down to maybe 10 versions of the drug, and then you come here with maybe 3 versions of the drug, and then you go into mice and another mammal, so at least 2 mammals, and then humans, and so on. So, not an easy job. Okay. So laser Doppler, I said, works by shining the light into the tissue, and it gets bounced around. The light that is bounced around by the static, the tissue that's not moving, doesn't change its frequency, but the light that hits a blood cell will shift in frequency depending on how fast the blood cell is going. Just like a train that's coming to you on a track, the sound of the train is always the same if you're on the train, but if you're standing on the platform and you're waiting for the train, and the first one always goes flying by, it sounds to have a higher frequency as it comes towards you, and a lower frequency as it goes away from you. And that's because of what we call the Doppler effect. Okay? So the vibrations are coming towards me much quicker as the train is coming this direction. They're vibrating my ear slower when the train is going that direction, just because the train is going away. And so it's the same with the photons that go inside my finger. The ones that hit the static tissue are not changed in frequency. The ones that hit the blood cells change their frequency depending on how fast the blood cells are going. We cannot measure directly this change in frequency because it's 10 to the power of 14 hertz. What we can measure is the mix, the beat frequency. When the two frequencies mix together, you get the difference between the original frequency and the frequency of the Doppler scattered light, the light that's scattered from the moving cell. And so this is just a few kilohertz. It's in the audio range. And that beat frequency is what we measure. And if we map it by scanning our laser across the surface, we can map it out. So again, if I use my forearm, and the forearm skin is used a lot in the first sort of tests in dermatology and medical imaging equipment. If we look at the normal blood flow, we see something like this. If I block the blood flow by blocking the brachial artery, we can see blue is very low blood flow, red is very high blood flow, and you have yellow and green in between. So you can see low blood flow, and then I release it again, and actually you see higher blood flow than before. We call this a reactive hyperemia. So you have higher blood flow coming in that direction. I mentioned that laser speckle is very much related to that. It's a simplified version. In this case, instead of pointing a light beam at the tissue like that and looking at individual points and scanning until you get a picture of the whole hand. In this case, what you can do is you can illuminate the whole area, the whole surface of the finger, for example. It's that way. Okay, oops, can't find my finger. There it is. You can illuminate the whole field, and all you do in this case is you look at how blurry the speckles are. So those of you who know about lasers know that if I shine light onto the wall like that, we will have, if we look closely at it, you will have very bright spots and very dark spots, and we call those speckles. Okay? And if my hand was very steady, or if I put it on the desk and shine it here, those speckles would stay in the same place for a long time. Okay? But if I shine it on my finger, those speckles don't stay in the same place. They move around a little bit. And they move around a little bit because the scatterers in my finger are moving around. The blood cells are moving around. So on the wall, we have this very nice, expensive white paint, which is lots of tin oxide particles in it, okay, usually. And they're just scattering the light back. They have a roughness which is roughly the same size as the wavelength of the light. And so they generate those speckles. Similarly, the blood cells are here and they're scattering the light, but they're more, causing it to be a little blurred because over time the speckles are moving. And if you choose the exposure time of the camera correctly, you can color your image according to how blurred the light is. So if I squeeze off my finger like that and the blood cells aren't moving so much, then the blood cells aren't moving around so much, and the speckles won't be blurred very much. If I release it and the blood cells are moving around a lot, then the speckles are very blurred. So they've moved during the picture. So during the time the camera shutter is open, so to speak. Nowadays, of course, you're using a digital camera, but the idea is the same. If the shutter is open for about 5 milliseconds, then the cell has moved during that time, and so has blurred out the image. And so what these people in Moore Instruments are doing is they show blue when the speckles are quite visible, individual speckles, and they show red when the whole area is blurred. That's what they do. And so you can show images, not actually very nice so nice in humans like that because they don't see very deeply, but in things where vessels are exposed, I think this is probably rat mesentery or, oh sorry, it's a mouse spinal trap, that's what it says there.